Here's a review problem on periodic motion from the AP Level C exam from the year 1986, problem number 3. If you want to hit pause so that you can print out your own copy and work along and take notes, feel free. You can hit pause now and resume when you're ready. Okay, so welcome back. This problem then is all about a spring that is not governed by Hooke's law. We're told that the force is proportional to x cubed. So for a typical spring, the ratio of stress to strain, in other words, the ratio of force compared to displacement, has some part of that graph that appears linear. And that range is referred to as the proportional limit for the spring. Beyond the proportional limit is the elastic limit, where the relationship between stress and strain might go nonlinear. In this case, there is no linear relationship between force and displacement. Instead, it follows this cubic relationship. So, given that information, we're told the spring, like so many springs we've investigated in this unit, is placed on a horizontal frictionless surface. When the spring is relaxed, the block sits at its equilibrium position. The block has mass m, and there's a spring constant k. In this case, k would not be in newtons per meter. K must be in units of newtons per cubic meter. In any case, if we pull this object back some distance, so it momentarily sits at the position x equals positive a, we need to figure out the potential energy, how fast the block is going to go when it passes back through the equilibrium position. For sure, the maximum speed must occur in the case when x equals 0. And lastly, we want to determine what's the displacement of the mass when the potential energy and kinetic energies are equal to one another. That's equivalent to saying that the instantaneous potential energy is 1/2 of the maximum potential energy. The only way potential energy and kinetic energy could be equal to one another is if they're both 50% of the maximum energy. So let's do part A first. Potential energy, U, is equal to negative the work done by the spring. So don't confuse that with the work you would have to do if you reached in with your hand and you pulled backwards. Sorry for the bad drawing of the hand. There's work done by you, which would be positive, because your force and the displacement would point in the same direction. Instead, we're being asked for a calculation of potential energy, and that's based on this definition that change in potential energy is always the negative of the work done by the conservative force. So even though this spring is not an ideal spring that's governed by Hooke's law, it still represents a type of force that is conservative. It doesn't, as that force is engaged, it doesn't tend to waste any energy into thermal energy. So work, in turn, is the integral of force and displacement. Our limits of integration are as the spring is stretched from the equilibrium position to this full amplitude A. So the potential energy must be the negative of the integral of negative kx cubed dx evaluated from 0 to A. So the negative signs cancel out, and our potential energy is, well, think of the integral as the antiderivative, and then you can see pretty easily our potential energy is going to be 1/4 k x to the 4th. We should evaluate this from 0 to A to give us 1/4 k a to the 4th. So there's our answer to the first question, the potential energy in the spring at the instant the mass is released. Let's figure out the maximum speed, and we'll get our answer to part B based on the law of conservation of energy. So there's a initial point A when the energy is all potential and equal to this amount, and then there's a point B where the potential energy is now down to 0 when the object reaches the equilibrium point, but the energy has been converted all to kinetic. So the maximum potential energy has been converted into maximum kinetic energy. This means that 1/2 mv squared must equate to this value 1/4 k a to the 4th. I'm so used to writing 1/2 k a squared for maximum energy of a spring, but this is a different type of spring altogether. If we multiply both sides of this equation by 2 and divide by m, we find that v squared is equal to k a to the fourth divided by 2m. So our maximum speed is equal to the square root of k over 2m times a squared. At this point, if some numerical values were given, we could plug in, but this is strictly an algebraic expression. Part C, what's the displacement when the potential energy and kinetic energies are equal? So like I said, we can rely on this expression as a way to solve the problem. If the potential energy is half of its maximum value, then the kinetic energy makes up the other half, and the two forms of energy would be equal to one another. So for the instantaneous potential energy to be half of the maximum potential energy, 1/4 k x to the fourth would have to equal 1/half of 1/4 k a to the fourth. K cancels, 1/4 cancels, x to the fourth is equal to 1/2 a to the fourth. Take the fourth root of both sides of this equation, and we get x is equal to the fourth root of 1/2 multiplied by a. You can grab your calculators and verify. This corresponds to x is equal to about 0.84 of the amplitude, 84% of the amplitude. Okay, last question. The amplitude of the oscillation is now increased. So instead of pulling it back, this original amplitude, what if we pulled it back even farther than that and let it go? Would it still have the same period of oscillation as it did the first time we released it? Well, for ideal springs, hopefully you know that period is independent of amplitude for the case of simple harmonic motion, for the case of an ideal spring, meaning a spring that's governed by Hooke's law, where F equals negative kx. But that's not the case here. F equals negative kx cubed. So I guess the idea behind period and amplitude being independent of one another, a lot of folks would think, even in the case of the ideal spring, that it must take more time to oscillate in case number 2 than it does in number 1, if in case number 2 the object has a greater distance to travel. What if you pulled it back farther in this case number 2? If it has more ground to cover, it should take more time, but you can make the counter argument, although it has to cover more ground with greater amplitude, it does so with a larger amount of force expressed at the ends, because force grows linearly with displacement. So the two have a canceling effect. As long as force grows with displacement in a linear fashion, then the amplitude washes out of the variables that have any dependency on the value for the period. But in this case, as the amplitude is increased, the force increases even more so. And so the acceleration that results increases far greater than the displacement, meaning it should take less time to cover greater ground if it accelerates that much more. In other words, this would be the long period, take much time to vibrate, and when it's pulled back even farther, this should be the smaller period of vibration. State whether the period of oscillation increases, decreases, or remain the same. The period of oscillation should decrease. Why? Because as the value of x increases, the acceleration increases even more so. Thanks for tuning in.